All right. I forgot my notes upstairs. I'm too lazy to go get them, so this might be a little bit more disjointed than usual, but we'll figure it out. All right, so today we are going to be talking about negative feedback amplifiers. Color, okay, that's right. And we're going to use our work on negative feedback amplifiers to define the ideal operational amplifier model. So by definition, a negative feedback op-amp circuit is one in which there is a feedback path from, and sorry, let me, VCC minus, VCC plus. So a negative feedback op-amp circuit is any circuit which contains a feedback resistor placed between the inverting input terminal and the output terminal. So just to be clear, this is V out, V minus, and V plus on here. This is the most common configuration for op-amp circuits. So we're going to spend 2 days on it instead of just one. We're going to start by analyzing a circuit, I think just one circuit based on time constraints, using the practical op-amp model, and then talk about the ideal op-amp model and how we can apply that to simplify our circuit analysis. And we're doing this because when what we saw with the positive feedback and the open loop circuits is when we knew that the output was going to have one specific state, it was either going to be VCC plus or VCC minus. We didn't have to do a heck of a lot of actual circuit analysis to figure out what was going on here. But in a negative feedback circuit, what's happening is that the output winds up subtracting a little bit from the input, and so we don't see extremely large gains, right? So even though our op-amp circuit has an open loop gain of tens to hundreds of thousands to potentially millions, we should see that in a negative feedback configuration, we can drive that gain down to specific values that are actually useful for amplifying a signal, effectively increasing the linear range over which the amplifier operates. So let's take a fairly straightforward circuit. Excuse me. And let's see. VCC minus, so it's powered with whatever it needs to be on. I'm going to put a 10 kilo ohm resistor here in the feedback position, a 5 kilo ohm resistor here, connected between the inverting input terminal and ground. And our input signal, Vn, let's say, is going to be 2 volts. And that's applied at the non-inverting input terminal. And here, we're going to take the output over an open circuit just because that will make something I want to do in a couple of minutes easier. So we are going to try to determine several different parameters, okay? Number one, something simple, the output voltage. Pretty straightforward there. Number two, AVCL, the closed loop voltage gain, okay? So we've been dealing with AVOL, the open loop gain. Now we're gonna find what the closed loop gain of the system is. And this wasn't an appropriate thing to find when we had positive feedback, because we saw that we were always operating effectively in saturation. And so changes in the input voltage did not create subsequent changes in the output voltage. So there was really no way to measure the gain. In a closed loop system, our voltage gain should be simply V out divided by V in. Okay. I want to find also our differential voltage VD, which will be the voltage present at the non-inverting input terminal minus the voltage present at the inverting input terminal by definition. Then I want to find Rn first. So this is the input resistance seen by our input voltage source. So it's the Thevenin equivalence resistance of the entire network as seen by our 2-volt input source. And then lastly, lowercase r, I want to find R out, which would be the resistance seen looking into the output terminal of this device. And we'll talk about how we're going to measure those things specifically momentarily. Excuse me. So these are 5 different things that we can look at that we really couldn't have looked at in any of our other amplifier models. And this is going to help us understand what's going on and how to apply our ideal conditions shortly. So we're going to use the practical op-amp model first. So in the practical model, here I have my resistance Rn, and I guess I need to give you guys values for this stuff. So we're going to solve for all of these under the conditions that AVOL is 10 to the 5, Rn is 1 mega ohm, and R out is 50 ohms. So these are the parameters of our op-amp. This is pretty similar to what you would see for a general purpose op-amp like the MUA 741 op-amp created by Texas Instruments. Because I have feedback from the negative or the inverting terminal to the non-inverting, or excuse me, from the inverting terminal to the output, I'm going to make this top node be my inverting input terminal. And this bottom node will be my non-inverting input terminal, which means VD will have this polarity. So I'm just flipping that resistor upside down to make my practical circuit look less wacky. That's all I'm doing here. All right. AVOL times VD goes there. Here is capital R out. So my output voltage in the figure is defined as the voltage drop over the open circuit at the output. So this is going to be V out. Ground. Between the non-inverting input terminal and ground, I see my 2-volt source. Between the inverting input terminal and my output, I have my feedback resistor, which is 10 kilo ohms. And lastly, between my inverting input terminal and ground, I have my 5 kilo ohm resistor. Like so. So this is my circuit using the practical op-amp model. Anybody have any questions about where any of these elements came from? Let's start there so that we're all on the same page here. All right, nobody has anything? Okay, so let's see. What nodes are we going to have to utilize here? Well, I think we are going to have to look at just KCL at the at the inverting input and at the output. So I'm going to need this current plus this current plus this current. Set it equal to 0 gives me one equation. And then this current plus this current equals 0 gives me another equation. In your homework, I'm going to give you a load resistance that you would actually have to include in your practical model and find the current for this as well. But for this one, we're not including that. So I just want to be clear, when that shows up in your homework, don't just randomly ignore it, because that's wrong. It's not going to change your answer a whole heck of a lot, you'll find out, but it's still wrong to ignore. All right. So let's see what we got here. KCL at our inverting input terminal. We are going to have V minus over 0, or excuse me, V minus minus 0 over 5 kilo ohms plus V minus minus the voltage present at our non-inverting terminal, which is 2 volts, divided by Rn, or what was the value of that? 1 mega ohm. So I'll just write it as 1 mega ohm. Make life a little bit easier. And lastly, we're going to have V minus minus V out divided by 10 kilo ohms is equal to 0. We do KCL at our output node. We have V out minus AVOL 10 to the 5 times VD, which is 2 volts minus D minus. So because the voltage present at node V plus with respect to ground is 2, the voltage present at inverting input terminal with respect to ground is nodal voltage D minus. This is divided by our output resistance of 50 ohms. And let's see here. We also have the current through the feedback loop. V out minus V minus divided by 10 kilo ohms is equal to 0. 2 equations, 2 unknowns. So now we got to take a minute or two to solve this guy. So let's stop. All right, so the coefficient for V minus is 1 over 5,000 plus 1 over 1 million. 1, 2, 3, 4, 5, 6 zeros plus 1 over 10,000. My coefficient for V out. And my first equation is negative 1 over 10,000. And my constant term is 2 volts divided by 1 million ohms. In my second term, my coefficient for V minus is going to be, so I have negative 10 to the 5 times 2 volts minus V minus. So negative 10 to the 5 times negative V minus gives me positive. So I have 10 to the 5 that's 100,000 over 50 minus 1 over 10,000. My coefficient for V out is 1 over 50 plus 1 over 10,000. And lastly, my constant term is going to be 2 volts, so 200,000 over 50. So that's 2 volts times 10 to the 5 divided by 50 ohms. When I solve this guy, I get 1.99939.802 volts. Normally wouldn't keep up with that many significant figures, but I'm doing it for a specific reason right here. And our output voltage is 5.999818803 volts. So we've answered the first of our 5 questions. What's the output volt? Something really dang close to 6, right? 5.998 volts. So that's one thing taken care of. How are we going to find the voltage gain? Specifically, the closed loop voltage gain. I defined it above as simply V out divided by V in. So that would be 5.999818803 volts divided by 2 volts. $2.999909402 volts per volt, really close to 3, obviously. And our differential voltage VD, which is V plus minus V minus, is simply 2 minus that 1.999, etc. So that gives me 60.198 microvolts. So 2 minus this number is 60.198 microvolts. All right, so we have determined our output voltage is roughly 3 times the size of our input voltage for this particular configuration. And our differential voltage is 60.198 microvolts. So do me a favor real quick, just as a sanity check. 60.198 microvolts times our voltage gain of 100,000 is going to be what? Voltage gain is 100,000. 6.0198 volts. Okay, so not the same as our output voltage. Is that okay? So does it make sense that V out is close, but not equal to AVOL times VD? Sure, that feedback resistor right there says this V out is not going to be the same as this because there is current flowing through our output resistor, right? So we're seeing some small perturbation here because of our output resistance. Perfectly okay, just wanted you guys to be aware of it so that if you think, oh, I could check my answer this way, you kind of can't, all right? Just to be real clear. All right, so the next thing that we need to determine is the input resistance seen by our input voltage source. And so I would argue successfully that we can use effectively Ohm's law here, okay? And so what I mean by that is that our input voltage divided by this input current should give us the resistance seen by the network. That's just good old Ohm's law, right? I'm just treating everything connected to my voltage source as a black box network. So effectively what I'm doing is this. I have a network. If I apply some voltage source Vs, the resistance of the network connected to my voltage source is the voltage drop over the terminals of the network divided by the current flowing through the network. Literally Ohm's law. Okay, nothing wild or crazy there. So let's see, what are we going to have here? Rn is going to be 2 volts divided by, all right, so how am I going to determine that current IN? What can I do now that I have the information that I presently know? Do I know the voltage at this node? Do I know the voltage at this node? Do I know this resistance step? So why can't I just do that? Right, so VD divided by R, capital Rn. Okay, let's see. Let me store this as a variable. All right, so I have 2 divided by VD, which is 60.198 microvolts, and that is divided by Rn, which was 1 mega ohm, right? Yeah. .322 and some change times 10 to the 10 ohms. So 33 giga ohms. That is the input resistance seen by my op-amp circuit. All right. For my output resistance, we're going to do something similar as well. So we know that the Thevenin resistance is simply the open circuit voltage divided by the short circuit current, right? Anybody got any beef with that? So if we're looking for the Thevenin voltage, or excuse me, the Thevenin resistance looking in through the output terminal, we already know what VOC is because that's the output voltage we calculated originally. Exactly why I didn't include a load resistance. Now we just need to figure out what that short circuit current would be. So we would do that by, let me use a different color here, pink. Shorting these guys and determining this current I naught. What that is, or how that changes what we have here. So let's see. V out by definition is 0 volts. So I could say that I Norton is going to be, oops, not what I wanted to do. This current in purple plus this current in purple added together. So I'm saying that my Norton current is going to be me reevaluating this guy, and then I find out what AVOL times VD divided by R out plus V minus divided by 10 kilo ohms will give me my Norton current. Anybody have any questions, comments, concerns about what I'm doing there or why I'm doing it? Perfectly reasonable if you don't follow what's going on. I'd rather stop and talk about it than go on while you guys are just sitting in the dark. Any questions about what I'm about to do? Okay. So I no longer need to do anything having to deal with this second equation down here because everything is sorted out, right? I know that V out is 0, so these guys really don't apply. So I'm just going to solve this guy for V minus, which will let me determine VD, and then that's all the information I need to be able to solve for my Norton current. So let's see, numerical solver, one equation, one unknown. So I have x over 5,000 plus x minus 2 over 1 million plus x over 10,000 I don't know why it gave me a error. That's just simple math. Equal to 0. All right, so in this case, just to be clear here, we're solving for R out, lowercase r out. So I get VD, and I'm going to call it, or excuse me, V minus Norton, I'll call it, because I was going to do prime, but that would be confusing, is 6.644 millivolts. I Norton, just to be clear here, is AVOL times VD divided by R out. AVOL is 10 to the 5. VD is 2 volts minus 6.644 millivolts divided by capital R out is 50 ohms plus V minus 6.644 millivolts divided by 10 kilo ohms. So let's see what we're going to get when we do that. Should be a really large number. $3,986.711 amperes. So short circuit, a whole heck of a lot of current. Now this is purely theoretical. An op amp could literally never carry that amount of current. It would burn itself up. But we're just trying to find the output resistance we see. The theoretical concept. R out is V Thevenin, or the open circuit output voltage that we calculated at the very beginning, divided by I Norton. So that's 5.999818803 volts divided by 3986.711 amps. $1.505 milliohms. run. So I just want to look at things here real quick. The input resistance seen by the input voltage source is 3 times 10 to the 10. So that is 3,000 roughly times larger, sorry, 30,000 times larger than the largest resistance in our system, which was the capital R in of the op amp at 1 mega ohm. And R out was 1.505 milliohms, which is on the order of a little over 1,000 times, I think it's 5,000 times smaller than the smallest resistance in our system, which was capital R out of 50 ohms. So now we are going to talk about the ideal op amp model, okay? So if you recall from our first lecture, when we had our black box amplifier circuit, this is the input voltage across the amplifier. This is the output voltage across the output of the amplifier, connected to some load resistance, RL, so such that we get an true output voltage of the system, VL, as a function of time. And over here on the right-hand side, we had a, or excuse me, the left-hand side, we had a practical source, RS. With our source voltage, Vs of t. And if I am not mistaken, we said that the ideal operation of this system is that VL of t will be AV, some voltage gain, multiplied by Vs of t. So in a perfect ideal world, this amplifier would work in such a way that our output voltage, VL of t, the voltage drop over our load connected to the system, would simply be the source voltage scaled up by some factor. So if we look at our practical model representation connected to this system, so here's our practical op amp model. Across my output terminals, I'm going to have some load resistance, RL. Let's see, I'm going to connect V minus, that's not what I wanted to do, to ground here. And Vs of t. So what we are about to do is use our knowledge of circuit analysis to figure out what values of R in and R out will cause the system to behave in exactly this fashion. Okay? So let me ground this guy here. So let's start. That's going to be slightly awkward, but I'll leave it as this, actually, VL of T. Okay. So from our ideal response of this system, where we want our load voltage to be some voltage gain multiplied by Vs of T, we need to figure out two things, really. How to pass Vs of T to this side of the system unchanged, and then how to get Vs to be multiplied by this voltage gain without any other changes, because that will give us this exact transfer function. So my question to you all is, what value of Rn makes Vd exactly equal to Vs? There's one value that doesn't. So if we put 0, that means V plus and V minus are the same node, which means Vd is 0, and Vd of 0 is not the same as Vs of T. So go literally the exact opposite direction. Infinity, right? So if Rn is an open circuit, Vd is exactly equal to Vs of T. So in an ideal system, Rn is equal to infinity. Now, if we figured that out, make a simple kind of substitution note here, Vd is going to be replaced by Vs of T. Excuse me. How do I make VL of T be exactly equal to AVOL times Vs of T? What value does R out have to have? 0. Color. The last thing, which we can't really glean from this at all, is that we would want our open loop voltage gain to be infinity volts per volt. There's really nothing that we can do to derive that other than just say, in an ideal case, we get an infinite amount of gain. That's not terribly important. Now, that's the open loop. So we want our input resistance for an ideal system to be infinity and our output resistance to be 0. Now, we can analyze the circuit using those values, and we'll do it. Actually, we'll do that right now because it'll help us with something. So we're going to analyze the exact same circuit we did a couple of minutes ago with Rn infinitely large and R out infinitely small. So this is infinity ohms. So it looks like a open circuit. This was V minus, this was V plus because we're employing negative feedback. ABOL times VD goes right there, where this is VD. Short circuit here. Feedback resistor. $10 kilo ohms. Two volts goes here. And 5 kilo ohms goes here. This is the only part of the lecture I'm nervous about not remembering what I'm supposed to do. So we'll figure it out. Excuse me, I'm just trying to think here real quick because I know. All right, let's do what we did the last time. See what falls out of it. So if we do Kirchhoff's current law at the inverting input terminal node, we get V minus over 5 kilo ohms plus V minus minus V out over 10 kilo ohms is equal to 0. Because we know the current flowing through this infinite ohm resistance must be 0 by definition. If we do KCL at our output, we get V out minus V minus divided by 10 kilo ohms plus, actually we don't have to do that at all. We don't do KCL at the output because there's a supernode there. That's the problem there, okay? So we know that V out is going to be exactly AVOL times VD. In a, okay, here's where, this is what I was forgetting. Sorry about that. That means that VD is equal to V out divided by AVOL. Anybody got a problem with that? A little bit of algebra there. Well, in an ideal op amp, AVOL is infinity, so we have our output voltage divided by infinity, which means VD must be 0. So the difference between our input voltage in an ideal op amp circuit has to be 0, which means V plus minus V minus is 0, or V plus is equal to V minus. So this is what's called the voltage constraint relationship. I'm going to put a box around it. Once we know that, V plus is obviously 2 volts, and so that allows us to solve for our output voltage of V out pretty trivially, right? So applying our voltage constraint relationship, which means we would sub in 2 volts here and 2 volts there, we get V out is equal to 6 volts. I didn't do the math on that. You're free to do it if you want to, but that is exactly how it's going to work out. So my question to you guys is, how much different from a results standpoint is the ideal model where R out is equal to 0, R in is equal to infinity, and AV, open loop, is equal to infinity. How different is that from the model we used using actual parameters? Negligible, right? Yeah, so we got 5.9998 volts for output, which is dang close to 6. We got 60 microvolts for VD, which is pretty dang close to 0. We saw that the input resistance seen by our voltage source wasn't infinite, but it was significantly larger than any voltage, or excuse me, any resistance actually in our system. And we saw that our output resistance was really, like, thousands of times smaller than any resistance in our system as well. So the ideal op-amp model is actually a very, very good approximation of the practical op-amp model in any negative feedback circuit, specifically in only negative feedback circuits, right? And it's because we're bringing the gain down to an acceptable level to where we can actually predict what's going on. So it's not just swinging from the output voltage to the input voltage. So we can use these relationships that we've developed to give us two simple rules for ideal op-amp circuits, and we won't have to use the practical model for them again. All right, so for a negative feedback circuit using the ideal op-amp model, the circuit behavior is governed by two rules. Number one comes from our voltage constraint equation. There can be no difference in potential between the input terminals. This is just a fancy way of saying V plus is equal to V minus. Voltage present at the non-inverting terminal has to be exactly equal to the voltage present at the inverting input terminal. And rule number two says that there can be no current flowing into or out of excuse me, the input terminals. And this is because Rn is equal to infinity. So we're assuming that effectively there's not a conductive path. Now, what's interesting about that, if we look at our practical op-amp model, we say that no current flows through here. Well, that makes sense because we were considering Rn infinite. But we're also saying that V plus must be equal to V minus, which means this guy is actually behaving like an open circuit and a short circuit simultaneously. Weird. We're not going to go any further than that. It's just an odd thing that is a result. But if we apply these two simple rules, analyzing negative feedback op-amp circuits actually becomes very trivial. It takes, I think it's 4 steps. So I'm going to take a generic circuit. This is kind of kicking off the next lecture, technically common op-amp topologies. So let's say that I have, let's use the exact same circuit we just did, but make it generic, okay? negative feedback, or excuse me, negative, positive. We're going to assume again that VCC plus and VCC minus are sufficient to power this guy. We have a resistor in the feedback position. We're going to call this guy R2. We have a resistor here. That's R1. This terminal is grounded. Here's where our input voltage is applied. And we could just as easily do this with numbers or not. So I'm going to do it without, okay? So there's 4 very trivial steps to analyzing any negative feedback op-amp circuit. Step 1, apply op-amp rule number 1. So what that means is that this voltage, V plus, must equal to Vn, then this voltage, V minus, is also equal to Vn. Pretty simple. Excuse me. For rule number 2, we apply op-amp rule number 2. So that means that this current is 0 amps, and this current is 0 amps. Rule number 3. Determine V plus, the voltage present at the non-inverting input terminal. Because this guy is so incredibly simple, we've actually already done that. We literally just applied a voltage source there, so it couldn't be anything else. So that guy's a gimme. And then number 4, apply Kirchhoff's current law at the inverting input terminal. So in doing that, let me use pink. We would have this current plus this current equal to 0, right? Because we know that no current can branch off and flow into the input terminals. So this tells us that Vn divided by our resistor R1 plus Vn minus V out divided by resistor R2 is equal to 0. I'm going to do a little bit of algebraic manipulation here. So this is Vn over R1 plus Vn over R2 is equal to V out over R2. This is the same as Vn times 1 over R1 plus 1 over R2 times V out over R2. So this is Vn times, let's see, R1 plus R2 divided by R1 times R2 is equal to V out over R2, which gives us finally V out is equal to Vn times 1 plus R1 over R1 plus R2. Do that algebra right? I know that the final answer is correct. I need to look at my algebra real quick to make sure I didn't make some dumb mistake here. Yeah, that seems right. All right. So this is our input-output relationship for any circuit that looks like this. So for example, in the problem that we just worked, where Vn was 2 volts, R2 was 10, R1 was 5 kiloohms, we should get 2 times 1 plus R2. There is a mistake there. Sorry about that. 2 times 1 plus 10 over. Oh, I have it right. 10 over 2. Why is my brain going there? Oh, that's wrong. Oh my God, I feel like a jackass right now. R2 over R1. All right, so let me just double check the algebra here because I feel like a complete idiot. So I'm going to have R2 multiplied by R1 plus R2 times R1 over R2. So that's going to give me R1, R2 over R1, R2 plus R2 squared over R1, R2 is the same as 1 plus R2 over R1. There we go. Okay, sorry. Total brain fart. That's what happens when I jump ahead instead of actually doing the math. All right. So now, sorry, this is 1 plus 5 over 2. 1 plus 10 over 5, so 1 plus 2, 3 times 2 gives us 6 volts. And there we go. This is how all of this particular type of circuit behave. And we can apply these same 4 steps to practically any other configuration. Even when there are multiple op amps, we can do this exact same thing and still be okay. And we'll show that when we get to cascade op amp circuits, I think next Wednesday. I know we're ducking out 15 minutes early today or thereabouts, but apparently my brain is fried because I can't do simple algebra at this point. So I'm going to let you guys off the hook a little bit early today. But you can practice this. I mean, this method that we've just derived is exactly what we did in circuit 1. We now can justifiably do it because we understand what the restrictions on it are. Okay, so homework 3 got put up on Wednesday. I'm going to post homework 4 today. Like I already have it made out, I just need to put it up. That will be on positive feedback circuits. Homework 5 will probably put up on Sunday. That is going to be on negative feedback circuits. So this lecture and the common op-amp topologies lecture that comes next, because it's all based on negative feedback. So there will not be an extra homework after the next lecture. That's all rolled up into one thing, and I think that'll get us on track. Alrighty, you guys have a great rest of your weekend. I apologize for A, forgetting my notes, and B, having a total brain fart when doing algebra here. So I hope you forgive me, and I'll see you guys on Monday, because today's totally Friday.